Welcome back. In this video, we're going to talk about skeletal notation, which is also called bond line notation. Before we dive into what skeletal or bond line notation is, let's first revisit Lewis structures. When we looked at Lewis structures before in general chemistry and early on in organic chemistry, we were drawing small molecules, so Lewis structures, they were fine. They were perfectly appropriate. Now, as we start to get into bigger structures, you're going to get very tired of drawing Lewis structures quite quickly. Imagine I asked you to draw this structure where you have a plethora of carbons. And if I asked you to draw the Lewis structure for it, where you had to draw each individual bond to hydrogen and you had to draw each hydrogen in, you'd get really tired quickly. And you would ask, is there a faster way to do this? The answer is yes. There's two faster ways. One is called the condensed structure, and then the other way is the skeletal or bond line structure. The condensed structure works like this. What you do is you look at the carbon and you see that you have 3 hydrogens attached to that carbon. You draw the carbon and you condense the bonds to the hydrogen by not drawing them. You're saying I have 1 carbon and 3 hydrogens attached. Then if we look at the subsequent carbon, this one right here has only 2 hydrogens attached. And we continue this until we've drawn in all of the carbons. So we just keep going. I'm just going to count really quick, make sure I got the right amount. So that's 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And even this, honestly, takes too long to draw. The other thing that I don't like about this condensed formula is when you start bringing in double or triple bonds, you have to really kind of look at them as a puzzle, where the condensed structure, if it's only showing a CH instead of a CH2, you have to know there's a double bond there, and that's very obnoxious. What I like to do, and what most chemists like to do, as well as chemistry textbooks, is draw in skeletal or bond line notation. I'm going to take the structure that we've drawn here, both in Lewis and condensed, and convert it into skeletal or bond line. And you always go back and count. Make sure I have 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. Now you're looking at this thinking, how the heck does that show an 8 carbon chain? And that's what we're going to get into next. Let's look at the rules for skeletal structures. When we see this zigzag format, every single bend is a carbon atom. This is a carbon, and this is a carbon. So bends represent carbons. The end is a carbon. Where I've highlighted in blue are 2 different carbons. So ends and bends are carbons. We're also going off the logic that each carbon makes 4 bonds. Of course, that's unless there's a positive formal charge, then there's only 3 bonds. And if there's a negative formal charge, there's 3 bonds in a lone pair. So the hydrogens are assumed. This is why you needed to spend so much time making sure that you had some basic stuff down, like formal charge and recognizing that carbon is tetravalent. Because knowing where the hydrogens are now is going to just follow a pattern. You're going to have to look at an end carbon, like the one I'm pointing to, and say that carbon is bound to only one other carbon, the one I'm circling in green. Because that carbon is bound only once to another carbon, it needs 3 more bonds to become something that has 4 bonds like tetravalent carbon usually has. Therefore, there are 3 hydrogens on this carbon. This logic is something that we're going to practice in exercises at the end of this video. We're going to cover some more rules where first I'm going to show you how double bonds are drawn. When you draw a double bond, you're usually still drawing a zigzag if it's in a long chain. When you draw that double bond, you're just drawing another line on top of your zigzag, like the one I just highlighted in yellow. When the double bond ends, there's a carbon here, and where it starts, there's a carbon. Where I've highlighted in blue are the 2 carbons involved in the double bond. Triple bonds are a little bit trickier because triple bonds are meant to be linear. And so this is 180 degrees, therefore we don't draw as zigzag. Triple bonds are also trickier because when you're drawing them linear, people will tend to draw them in skeletal notation in two different ways. One way I've drawn here, where notice where I'm highlighting in blue, there's a space between the triple bond ending and the rest of the structure. This is representing a carbon-carbon triple bond with a CH3 on this end and a CH3 on this end. Because remember that every end is a carbon. Therefore, these are carbons that are only involved in one bond, so they have 3 hydrogens attached. The other way to draw a triple bond is drawing one big long line and then drawing the pi bonds on top and bottom. Usually, if your teacher sticks with one of these ways, when they accidentally draw the other way, people don't recognize that this and this, where I'm highlighting in blue, are still carbons. So no matter which way your teacher draws it, you need to make sure that you are aware that with triple bonds, where the 3 lines stop is a carbon, even if the exterior, that middle line, keeps going. Now I want to practice showing you something in Lewis structure and taking it into skeletal notation. We have 1, 2, 3, 4, 5 carbons here. When I try to translate this to skeletal notation, what I will do is start by drawing my zigzag. When I start with my zigzag, that first line that I draw is 2 carbons because I have 1 carbon here and 1 carbon here. When I'm counting in my head, I draw that line, and in my head I say 2, 3, 4, 5, and I have 5 carbons, just like the Lewis structure on the left. And it took a lot less time to draw. When you're drawing this, part of the reason we get away with skeletal notation is because most of the time the carbon-hydrogen bonds aren't doing a whole lot. They're not a really important group in chemistry for the most part. Sometimes, yes, we will abstract a hydrogen and pull it off with a base and it'll be involved in a reaction. But for the most part, my chemistry teacher used to call this junk. He'd say, "Caitlin, don't look at the junk. Don't let the junk distract you." And he meant the CH stuff. When we're looking at the skeletal notation, sometimes what you want to do when you're first beginning is just to go back and double count. So even though I started and I said 2, 3, 4, 5, I'm just going to go back and double count and make sure I have 1, 2, 3, 4, 5 carbons. Now I want to draw something that has a triple bond. Drawing the triple bonds can be a lot trickier. First, I want to draw it wrong, and then I'm going to draw it correctly. When I look at this structure, I see 1, 2, 3, 4, 5 carbons again. The most common wrong thing is to draw your 5 carbons and put in your triple bond here. Now, the reason that this would be considered wrong is because you're not illustrating the 180-degree bond angle for your carbon-carbon triple bond. In other people's classes, they might not be that picky, but in my class, I expect you to draw the triple bond in a linear fashion. Sometimes it might be helpful to actually draw out wrong first when you're starting and then correct it, because triple bonds do look really weird. What you can do is start with your triple bond and make sure that it's drawn in a linear fashion and say, hey, here's my triple bond. I have 1 carbon right here, which is the carbon that I just highlighted over in my Lewis structure. And that carbon has 1 CH3 attached to it, so I know I have 1 CH3 that way. Then my other carbon, right here that I'm circling in green, is going to be over here where I'm circling in green on my Lewis structure, on my skeletal structure. Then I have 2 carbons attached, and remember every bend is a carbon. So let's go ahead, I'm going to erase some of that work and I'm going to go ahead and I'm going to count them. 1, 2, 3, 4, 5. So I have 5 carbons where between carbon 1 and 2 there's a single bond, and between carbon 2 and 3, there's your triple bond. This is the correct structure for skeletal notation. When we are working in skeletal notation, we want to make things kind of look pretty. What that means is having angles that look nice. When we have double bonds, if I'm going to take this structure on the left and redraw it, it's going to redraw in skeletal notation like this. Look how nice and simple that is. It went from this huge structure that I could barely make it fit inside the words to something that just took a second or two to draw. One of the things that you're seeing here is we're getting nice angles between the bonds that I've drawn. What we don't want to see, and what I'm about to draw is incorrect, and not incorrect, just not logical, is, this. I know that for you, because you're brand new at this, the one I'm circling in yellow might not look wrong to you because you don't know what really looks right or not yet. This one looks wrong to me because I know that the carbon here and the carbon here are sp2 hybridized and thus have a 120-degree bond angle. Then when drawing single bonds, directionality of the bonds doesn't matter. What this means is the skeletal structure that I drew on the left, I'm going to redraw. And when I redraw it, I can redraw it like this and it's still the same structure. Or I can redraw it like this and it's still the same structure. Or I could draw it even more ways. I could take this bond and point it up and it's still the same structure. That idea is really going to fold in heavily with constitutional isomers. A couple more rules. All your heteroatoms have to be drawn. Well, what's a heteroatom? A heteroatom is anything that is not carbon or hydrogen. So you have to draw in your oxygens, your nitrogens, your fluorines, your chlorines, and bromines, and so on. And if there's any hydrogens attached to those heteroatoms, those have to be drawn. So you're not drawing in hydrogens on the carbons, you're drawing in hydrogens on non-carbons. If we look at the structure on the left and we redraw it, what we'll see is this for skeletal notation. Right, I'm taking the carbon structure and I'm turning that into skeletal, but the oxygen and the hydrogen attached to that oxygen is still there. One of the things that we struggle with at the beginning of skeletal notation is remembering that carbon makes 4 bonds. What I mean by that is occasionally we get ourselves into trouble and we start doing stuff like this, where this carbon right here has way too many bonds. You can't do that. You can't have 5 bonds, right, pentavalent. And if you're gonna have 3 bonds and you wanna communicate that, you have to put in a formal charge. If there's no formal charge communicated, then that means that you are looking at something that has 4 bonds and you just have to watch out for accidentally drawing something that's pentavalent. Now I wanna give you an opportunity to try some exercises. Please take these 2 structures and turn them into skeletal notation. Pause me while you're doing that and then come back and we'll compare some answers. Now that you're ready to compare answers, let's walk through these. The first thing that you do for the first structure is you count your carbons. You got 1, 2, 3, 4 carbons. Remember that every end, so here is a carbon and every bend is a carbon. So what I'm highlighting on the right-hand side are my 4 carbons. If I just start kind of counting these to make sure that I have the double bond in the right place, I can start on the left and count 1, 2, 3, and 4. And over here I can say 1, 2, 3, and 4. And I'm showing in the skeletal notation that I have a double bond between carbons 2 and 3, and that's exactly what I'm seeing in the Lewis structure. If we look at the bottom structure and consider where the alcohol is, we have 5 carbons in this structure. The alcohol is on the second carbon from the left. And when I draw my skeletal notation, I make sure I have my 5 carbons. And you put in your OH. Now, I'm putting my OH on my carbon number 2 from the left, but honestly, if you would have put it from the right, let's draw that as well. So if you would have put the OH on that side, that's actually the same structure, it's the same compound, it's just turned 180 degrees. Notice how I also wanted to communicate that for the OH, you can either draw out the OH bond or you can condense the OH bond. We're still brand new, so I would really like you to put lone pairs on the oxygen, but you can see that when I'm in a rush, I leave off my lone pairs by accident sometimes. But right now, we should be good chemists and we should add those lone pairs. For this exercise, I want you to take a moment to pause me and add formal charges to these skeletal structures. Now that you've unpaused me, I want to show you how quickly you should be able to do this. Are you ready? Positive oxygen, negative carbon, negative oxygen, negative nitrogen. That's how fast you should be. And when you say, but you're the teacher, of course you're that fast. No, but seriously, you should be that fast too. And if you need some extra support with formal charge, I did make a video about formal charge and encouraged you in that video to make a formal charge table. That table is going to be very helpful. So make sure that you actually do that, because trust me, when I tell you, you need to be that fast. Let's do one more exercise. In this exercise, I have 2 different structures drawn and I have 4 total carbons highlighted. What I would like you to do is tell me how many hydrogens are on each of the highlighted carbons. Now that you're back, I want to show you how fast you're going to be able to do this as well. Eventually, you'll get to the point where you can just look at that and say there's 3 hydrogens here, and that there's 1 hydrogen here, and that there's no hydrogens here, and that there is 1 hydrogen here. Right now, you're not going to be that fast. Right now, what you're probably going to do is something that drives me bananas, but it's okay because you're learning, is students draw in these little tick marks on all of the carbons because it helps them visually. As we continue, we need to have so much practice that we don't draw those tick marks anymore, showing how many bonds are still left on those carbons. So if you did that right now, fine, that's great. That's what you need to do to understand the material. But as you keep going, I need you to practice more and get to the point where what you're doing is you're looking at that highlighted carbon. So let me focus on this highlighted carbon. And you're saying I have 1 bond attached to that carbon. So if I have 4 bonds for carbon and I have 1 attached, then that means I have 3 bonds left. And those 3 bonds have to be hydrogen because your hydrogen is assumed. Let's look at the second carbon. So the one I'm highlighting in green now, the one that's part of a double bond. Notice how that one in green has a double bond, right? So that double bond counts as 2 bonds. And then it has a single bond. So there's 3 bonds already on that carbon. Then you have 1 more bond left until you make 4 bonds, which means that bond has to be to hydrogen. So I know there's 1 hydrogen there. If we go over to the other structure and look at the carbon that is involved in a triple bond, there's 3 bonds already there. So right here, 1, 2, 3, and then 1 off to the left. So that's 4 bonds. That means there's no hydrogens present. Finally, the carbon that has the positive charge. Normally, carbons make 4 bonds, but when you have a positive charge, that means it only makes 3. You already have 2 bonds drawn here. So here is 1 carbon and 2 carbons that positively charged one is attached to. And so you only have 1 hydrogen left. So this is how we need to logic our way through it, but then have enough practice that we can just speed through it and be confident. We have one more section here with drawing structures in skeletal notation. I just want to review what the wedge and dash bonds are. When you see skeletal notation, you'll also see these wedge and dash bonds folded in sometimes when skeletal notation. Not all the time, but once we get to stereochemistry, you'll see them a lot more often. That wedge bond means that it's coming out at you. So it's coming out of the page. This wedge is saying that there is a CH3 there. How do I know there's a CH3? Because at the end of the wedge, if there's nothing drawn, it's the end of a skeletal notation, which is a carbon. So there's a CH3 there, and this drawing is showing that the CH3 is coming out at your face. Whereas this dash is also a CH3, and it's showing that it's going behind the plane of the page. So wedges come out at you, dashes go away from you, and if there's nothing at the end of the wedge or the dash, it's assumed to be a CH3. When we draw cyclic structures, like we're seeing down here at the bottom, we are still using skeletal notation, and what we will do sometimes is even include your wedge and dash bonds. So I could put a wedge here and I could put a dash here. If I wanted them not to be CH3s, I could put a bromine here and an OH here. Be a good chemist and put in my electrons. You're going to expect to use skeletal notation for the remainder of the semester. Let's wrap up. In this video, we looked at translating Lewis structures into skeletal notation, and we took it really slowly, making sure that we could really make sure you're able to do all of the exercises that we practiced and get really comfortable with those kinds of things, especially figuring out how many hydrogens are on each carbon. Make sure that you spend a lot of time working on skeletal notation because for the majority of the semester, we're going to be using it, whether you're in my class or not. Thanks so much. This is Katoni signing out.